In the last lecture, I introduced single and two qubit gates in the form of matrices, where the matrices were unitary matrices. So that helps us understand operators easily because we can just think of them as transformation of our qubit states. And since qubit states are column vectors, so matrices naturally helps us understand their transformation. However, when we are dealing with the many qubits, matrices become cumbersome because they exponentially scale with the number of qubits. If we have three qubits, their general transformation would require an 8 by 8 matrix and so on. And also, quantum computers actually they do not implement these matrix multiplications. Matrices are helpful when we are trying to simulate the action of quantum computers on, let's say, our laptop, because our classical computers they can take care of matrices very easily. So, to get an alternative representation, I'm going to introduce a new way of writing operators, which is called the outer product form, which physicists find very easy to handle because we don't have to deal with big matrices, and especially these matrices usually only have few non-zero entries. So even if the entries are not, there are more than few which are non-zero, the outer product form is very helpful. And also, the outer product form is much more intuitive, as we will see. So in this lecture, I will revisit single and two qubit gates that we discussed in the last lecture, where we worked with them as matrices, and we will now introduce the auto product form and express them in the auto product form. And also towards the end, I will introduce projection operators, which are helpful when we are dealing with the measurements. So let's start with the definition of the outer product form, and then we will express the single qubit and two qubit operators in the form of outer product. So outer product form, for a reference, is written here for a single qubit basis states. And you see that so far we had studied inner product, which was the product of this type where we had a row vector and a column vector. So for example, this is this, and this is this matrix. So this results in a scalar number because this row multiplies with this column, so we get a scalar number. And then we also had a tensor product, which increases the size of matrices. For example, if I have let's say we have this matrix, suppose 0 tensor 1. So this I can write as 1 0 tensor 0 1, and then this 1 multiplies both entries 1 by 1 0 1, and then this 0 multiplies both entries 1 by 1, and we get this matrix. And then there is this third type of product that we are now going to talk about, which is the outer product, and where we are essentially multiplying a column vector with a row vector. So this is a column vector because this is this, and then this is a column vector like this. And then we can do the usual rule of matrix multiplication. 1 multiplies by 1, we get 1, and then 1 multiplies 0, we get 0. 0 into 1 is 0, 0 into 0 is 0. So it means that wherever we see this matrix 1 0 0 0, we can replace it with this symbol. Similarly, this matrix can be replaced with this, and this matrix can be replaced with this, and this with this. It is sometimes bit difficult to remember, especially these two. These are easy because this 0 bra 0 cat this is this first one, and this 1 1 is just this lost, the other diagonal entry. But these diagonal, are sometimes people confuse these two. So as a sort of an aid to memory, you can think of this. We start with the 0 0 0 1, then 1 0 1 1. So this entry is 1 0, this one, and this entry is 1 1. So this is 0 1. And let's first write the one of the gates in this notation, and then we will uh, be able to see the use of this notation in a bit better way. So let me copy this as a reference to the next slide over here. So this would be a nice reference. All right, so let's start with the X gate, which is the simpler for us. So X was this matrix 0 1 1 0. So if I use this thing, so I have this non-zero entry 1, so this corresponds to this, so I can write this 0 1, and then there's this one over here, so I can write plus 1 0. So it means the outer product form this for this operator 0. Sometime instead of writing this bracket like this and then this bracket separately, some people just write this cross. So this is just for ease of writing, especially when you're writing on paper, but this always means this thing. So the next term is 1 0. So this is the outer product form of the operator. And let's see how does it help us in computations. So suppose I want to work out what happens when I apply x to this state 0. So this means that I apply this x to this state like this. And now after this, the product works the way that we already know. So this 0 is multiplied with this. So this 1 0, and this 1 is as it is, and then a 0 gets multiplied with this thing. So this we already know what it is because these are orthogonal states. So this is inner product. So inner product of 1 and 0 is 0. So we get 0. So this is just the usual scalar multiplication, and then this is 1. So this is 0 into 0 is the norm of 0 vector square. So this is 1. So multiplied by 1. So this goes away and I get 1. So we see that this notation very easily helps us. So similarly, let's say I want to work out what happens when x is applied to 1. So this means this plus, so this 1 inner products with 1, we get 1 into 1 1, and this 1 inner products with 0, so 1 into 0 is 0, so this term goes away. So this x applied to 1 directly gives us 0. So this is easy. Let's take another example. Suppose I have a z gate which was 1 0 0 minus 1. So this should be, because this is 1, so this corresponds to this form, and this is minus 1, so this corresponds to this, so minus 1 into 1. So our z operator can be written as like this. And let's see if I apply this z to 0, or we can work it out. So we can easily see that the 0 applies to this. Well, so this 0 has to inner product with this and with this term. So when the 0 inner products with this 0, so we get actually 1. So we get 1 here, and then minus 1, and this 1 inner products with 0 gives us 0. So we are left with 0. And similarly, when the z is applied to 1 here, we get 0 0 minus 1 1 1, and 0 into 1 is 0, and 1 into 1 is 1, so we get -1. So we can now see the utility of this form, that this actually gives us results quickly. So let's go to next empty slide. So let's see the Y gate. Our poly Y gate is, since this was in matrix form, 0 minus iota iota 0, and let's see if we can recall. So this minus iota is 0 1, and this iota is 1 0 place. So now if I want to see what happens when y is applied to 0, all I have to see, so you see 0 has to come from this side, and it has to inner product with this one and this one. So since this is 0, this is orthonormal to this, so with this its inner product goes away. So with this its inner product is 1, and I'm left with this term, so iota 1. So similarly, when y applies to 1, so essentially means that 1 is coming from this side. So this 0 into 1 would be 0. So 1 into 1 would be 1, and I'll be left with the minus iota 0. So we see that this notation actually has another interpretation as well. That this is just telling us how this state transforms to this state. So this one state transforms to minus iota 0, and the 0 transforms to 1 iota. So this is essentially the intuition or the operation of the gate is already encoded in this. For example, if you recall the representation for the X gate from the previous slide, so you can easily see that this notation is telling us that 1 goes to 0 and 0 goes to 1. So this is sort of an intuitive way of writing the form as well. Let's see the Hadamard gate. So Hadamard gate was specified by this matrix. So in the outer product form, this would be 0 0 plus 0 1 plus 1 0 minus 1 1. So this is the form of the Hadamard gate, and we can see what it does when it gets applied to 0. So when it is applied to 0, so this goes away, because 1 into 0 is 0, 1 into 0 is 0. So, and this 0 into 0 is 1, so I'm left with this 0, and I'm left with this minus 1. No, sorry, this I'm applying to 0, so this has gone away. So 0 into 0, this one 1, so I'm left with plus 1, so which is the plus state. So similarly, the H applied to one state will give us this state with minus sign. So this becomes the minus state. All right, so this is the outer product form representation for 1-qubit gate. Let's now go to multi-qubit gates. So for 2 qubits, we have 4 by 4 matrices. So if I write a general matrix, so it should be U11, U12, U13, U14, U21, and so on. So there are 16 terms, and we have to find the outer product representation for each one of them. And we can do this if we recall that our basis has these 4 entries, and this corresponds to this column vector, this corresponds to this column vector, and this corresponds to this column vector, and this corresponds to, which we found out after the tensor product between this 0 state and this 0 state. Now from here we can construct various matrices. For example, 0 cat, 0 bra would be 1 0 0 0, and then this would be 1 0 0 0. And let's do this 1 into 1 1, 1 into 0 0, 1 into 0 0, 1 into 0 0, then this 0 into 1 0, so all the rest are 0. Similarly, 0 0 0 1, with this it would be 1 0 0 0, 0 1 0 0. Let's see which of the element is. So 1 into 0 is 0, 1 into 1 is 1 0 0, and all the rest are 0. So this was 0 0 0 1, and 0 0 0 1 would be 0 0 1 0, and 0 0 into 1 1 . So the matrices are terms for these four entries, and then we can easily see that this would corresponds to 0 1 0 0. So this would be 0 1 0 0, and then this term would be 0 1 0 1. So this would be 0 1 0 1, and so diagonal terms would be the products of these cats with their corresponding bras, and the off diagonal terms would be the cross terms. So with this intuition, let's now go to the control X gate. So this was the control X gate matrix that we had last time. So we can now see that this should be the outer product representation for this thing, because this corresponds to this thing, this corresponds to this one, and this is this term, and this one is this term, because this starts, all of these terms have 0 0 on the left, all of these terms have 0 1, all of these terms have 1 0, and all of these terms have 1 1 on the left. Now let's see if this is the correct one or not. So, and just to make sure that everyone is on the same page, when I have written 1 0, this essentially means 1 tensor 0. This is like a shorthand for this 2-qubit state. Okay, so let's apply this CX gate to suppose 0 0 state, and we know what should happen. Because this is the control qubit, this is the target qubit, so this is in 0, so nothing should happen to this, so we should get 0 0. And let's see if this matrix does this for us or not. So this would be 0 0, and we know that this inner product is 1, and this inner product is 0, this inner product is 0, and this inner product is 0, because all of these four states are orthogonal to each other. We can easily check that if we multiply any of these two, if we take inner product, the answer would be 0, because they have 1 at different points in their position. So this means that all of these three inner products are 0, and we are left with only this. So similarly, if I apply Cx to 0 1, so when the 0 1 will multiply from the right, so this inner product is 0, the inner product with this is 1, so I get 0 1. The inner product with this would be 0, the inner product with this would be 0, so this is what we get. Now let's see what happens if we apply Cx to 1 0. So when 1 0 comes in here, so this inner product is 0, the inner product with this is 1 0 1 0 state, so this is 1, so I get 1 1. So this 1 0 with 0 1 would be 0, with this 0 0 also 0. So, and this is actually what we should get, because this is control qubit is in one state, so this gets flipped, 0 goes to 1. Similarly, if we apply Cx to 1 1, so when 1 1 is coming in here, so this inner product would be 1, so I'll be getting 1 0 non-zero, coefficient 1. So this inner product is 0, with this 0, with this is 0, so all of the other three terms go away, and this is what we should get. Okay, so this is the correct notation for this gate Cx. Let me just take this to the next slide, because I want to discuss this point separately. We'll come to it. So this actually is true, we should have figured it out already, because this, as we were discussing the intuition before, that we know that this is what the control X gate should do, that 0 0 state should go to 0 0, 0 1 state should go to 0 1, 1 0 state should goes to 1 1, and 1 1 state should go to 1 0. So we should have been able to write this inner the outer product form directly from this truth table, and let's see how. So this state has to go to this, so the state, so this left side is coming on the right here, is going to 0 0 plus, so this state has to go to this, so 0 1 has to go to 0 1. Now this 1 0 has to go to 1 1, so 1 0 has to go to 1 1, and the 1 1 state has to go to 1 0. And you see that this is exactly what is already written here. So the outer product form has another advantage, that if we are given a truth table, finding its matrix is actually hard, but finding its outer product form is actually very trivial. So because all of these states are orthogonal with each other, we can exploit this thing, because whenever there is a combined state and we are taking inner product from the right, if they're orthogonal, the inner product will be non-zero only with one of them. So it means that I can write all of these four terms independent of each other, because when a basis state comes from the right, it can only be non-zero, it can have inner product non-zero only with one of the term here. And so this input column goes on the right side and the output column goes on the left side. So this outer product form of operators have this intuitive sort of feeling. And now once we have this outer product form, I can actually write the matrix from here directly, because the matrix is easy to write. So this is 0 0 term, its coefficient is 1, so I put a 1 here. This is 0 1 0 1 term, it's a second diagonal term, I put a 1 here because there's a coefficient 1. This is 1 1 1 0, so 1 1 is at the last column, so this goes here, and it's coming at 1 0 position, so 0 0 0 1 1 0 and nothing here, and this is the 1 0 1 1 position. So in the third line, the last one, so this 1 1 corresponds to the last position. So converting this outer product form to matrix representation is then trivial. So writing the matrix directly is difficult, but writing the outer product form from the truth table of the matrix is easy. All right. So let me just discuss one point quickly that we didn't discuss in the last lecture, and that is that there are two types of two qubit operations. So let's say I have these two qubits sitting here. So one type of operation is this, that I do something to this qubit and do something to this qubit. In that case, the total operator, let's say some operator O, is the tensor product of individual operators that we have done something to this. So for example, this X operation was performed here and the Y operation was performed here. So then the total operation is the tensor product of two individual gates, where, so this is the first gate, this is the second gate, and then with the tensor product rules, I can write the joint matrix, and I can even convert it into the outer product form. So for example, this term corresponds to 0 0, sorry, not 0 0, it corresponds to 1 1 0 0. So this corresponds to, and there is a, let me write over here. So this corresponds to iota 1 1 0 0. So this is sort of the row term and this is the column. So the row level is 3. So this is like 0 1 2 3, and this columns are like 0 1 2 3. So 0 1 2 3. So row number 3 and column number 0. So then this term is minus iota row number 2 1 0 and column number 1, which is 0 1, and the next term is iota 0 1 1 0, and the last term is minus iota 0 0 1 1. So we have written this tensor product as the outer product as this operator as the tensor product of these two operators. And by the way, I can also write this like this as well. So this operator is 0 1 plus 1 0, because this is nothing but X operator tensor, and this operator is the Y operator minus iota 0 1 plus iota 1 0. And then there is second set of two qubit operations. So this is like the you can say the product operator, and then for example the control X gate. So control X gate cannot be written as just some gate on one qubit and some gate on the second qubit. It can be written as sum of terms like this, but not a single term where one term is operating on one qubit and the other term is operating on the other term. So these types of the gates, which are actually sort of true two qubit gates, because we cannot factorize them as single qubit gates. So here, even though this is a two qubit operator, but this can be factorized as two individual single qubit operators. All right. So let's see another application of outer product form, which is in constructing the projection operators. So we discussed in the first lecture that quantum measurements are different from classical measurements in that they disturb the state. Actually, we can really say that quantum measurements are measurements that project our essentially they're non-projective measurements as well, but they can also be written in terms of projective measurements in some higher dimensional space. So quantum measurements can be written as projective operators. And let me show what I really mean. So for example, if I have a single qubit, and let's say the qubit resides in some superposition state A0, B1, but when we measure it, after the measurement, the system will either be found here or it will be found here. So the system has been projected to one of these state. And this projection process, we can model it mathematically using projection operators. For example, the operator to project to state 0 can be written like this. Because what it does, that whatever state it applies to, it always projects it to state 0 with some coefficient. So similarly, we can construct a projection operator that projects our state to the one state like this, because when we apply it to the state psi, we get some coefficient times one state. So this is a projector that projects our state to one state, and this is a projector. This is a projector that projects our state to zero state. And similarly, we can construct higher dimensional, projection operators. For example, we can have a projection operator that projects us to a 2-qubit 00 state, or maybe we can have a projector that projects our state to a product state of 2 qubits, where one qubit is in superposition state plus and the other qubit is in the superposition state minus. Okay, so with this, our short introduction to the outer product form of operators comes to an end. And just to summarize, outer product form is intuitive because given the truth table of the operator, we can directly write the outer product form, and it's very handy as well, especially when there are few non-zero terms, because the matrix, for example, for a 2-qubit state operator, we have a matrix with 16 terms, but for example, for the control X operator, there are only 4 non-zero terms. So in the outer product form, there are few non-zero terms. But I think even a better reason is that initially, perhaps, and sometimes students start thinking that okay, the quantum computer is essentially implementing matrix multiplication, but that really is not the case. We are using matrices to represent quantum operations, but physically, in a quantum computer, when a gate is applied, it's just a pulse of light or RF pulse that is being sent to the system. So it's not really the matrix multiplication that is going on. However, when we do simulate quantum computers working or a quantum algorithm on our classical machines, people have developed simulators to simulate using matrices. So the outer product form sort of reminds us this thing, that quantum operations, they're not really matrix operations when they are happening physically. Even though both descriptions are mathematically totally equivalent, you can use either one to solve problems on paper or to analyze algorithms. So with this, we would like to conclude this short introduction, and I look forward to having you in the next lecture, where we will talk about rotation operators, both single qubit rotation operator and 2-qubit rotation operators, which are very important, especially when we are developing quantum machine learning algorithms, which in which we encode our data to a quantum algorithm using rotation operators.